All right, the last concept in chapter 15 is called Le Chatelier's principle. Up to this point, you should be able to write an equilibrium constant expression. You should be able to calculate it once you know the concentrations of all the substances at equilibrium, and you should be able to solve mathematical problems utilizing an ice table technique to be able to organize your thoughts and figure out what the concentrations of the substances will be when equilibrium is achieved. The last thing is Le Chatelier. Le Chatelier states down here in B that when a reaction is at equilibrium, if we disturb it and we change it from equilibrium, the reaction will shift to reestablish equilibrium. And that's what today's lecture is going to focus in on. Now, I'll have a homework on this key concept because you have the lab. The lab that is to be covered, and again, I did change the due date now. The due date for this is this upcoming Friday, which is the last Friday here in February. So, but the laboratory gives you that practical application of, as we make these different stresses, how the reaction will shift in order for equilibrium to be reestablished. Okay? Now, the first thing I want you to do is look at this table right here. And from that table, I would like you to go ahead and pause the lecture for a second and formulate two conclusions that can be drawn from the information from this table. Please pause the lecture now, formulate the conclusions, and then restart the lecture, and I'll give you the answers. One thing to note before you do this, if you were struggling with it, this reaction, the data, is looking at this reaction right here, which is called the Haber process, which is the formation of ammonia from its elements. All right, so utilize that equation, look at the data from it. The NH3 is a product, and be able to formulate your conclusions. All right, the two conclusions I'm hoping you came up with from the data is that in order for us to maximize the amount of ammonia that needs to be produced from this reaction, we'd want the pressure to be as high as possible and the temperature to be as cold as possible. And that would increase the formation of product, and the more product we get from the reactants, the better our profits will be too, because we'd need less reactants to form the products, in this case ammonia, which is a fertilizer. Okay? And Le Chatelier will help explain that. Now, in Le Chatelier, we look at three different factors to consider. We look at changing the concentration, which is what the lab did often. We look at changing in pressure, which our lab did not do that, which we'll talk about here, and what changing the pressure will do. And then lastly, changing in temperature, which was the fourth reaction mechanism change that I did, putting the cobalt solution into either the hot or cold water. So we did do a temperature example of it as well. The most common one is changing concentration. Looking down below, we can see that here. Initially, we are at equilibrium. Again, this is the Haber process. And again, this is how you write the expression. Products go on top. Their molar concentrations are raised to each of their balance coefficients. And that is the expression. Now, first thing I'd like to do is pause the lecture. I'd like you to calculate the value of the equilibrium constant under looking at the first initial set of conditions. So go ahead, plug in the numbers and see what you get right now. All right, you should have gotten a value of 0.0596. And again, when K is less than 1, that tells us product formation is not favored. We have a very low concentration of products compared to reactants. All right, now the change is we are going to increase the amount of N2 in the reaction vessel. We can inject it into it and see what happens to it. Okay? And by doing that, by increasing by 1, we have now changed the concentration of this guy to 1.399 molar. So by increasing that, let's see now what happens. Since we are no longer at equilibrium, we are now calculating what is a Q value. A Q value is what is the value of the reactants to products to reactants under the current set of conditions, and that is called the reaction quotient. So let's go ahead and plug that in. So now we're going to plug in 0.202 squared, but now our N value is going to be significantly increased. And this will be what happens immediately once we inject it. So now let's go ahead and plug in that value. And we get a Q value of 0.017. Okay, we're increasing the amount of reactant, and that is going to cause that number to drop. So in this case now, we have a Q value that is less than a K value. And this is the way I like to tell my students to write it. I like to have K written first and Q written second. Why? The way that the arrow points dictates which way the reaction is going to shift. So based on increasing the concentration of one of the reactants, the reaction has to shift to the right. We have to produce more products in order for that K value to be reestablished. And we can see that with the data, that the N concentration goes down, the hydrogen concentration goes down, and the NH3 concentration goes up from the previous set of equilibrium conditions. Now let's plug those numbers back in and see what the new value is. And if it is truly at equilibrium, this K value should be what it was initially. So go ahead now, I'm going to pause the lecture. You go ahead and calculate out and see if we get back to the original K value. All right, plugging in the new values, we get a value of 0.0602. Now you can see that's a little bit different, but we're only off by 6/10,000ths. That's really, really small. We in essence have the same K value. Due to rounding, we're not going to be able to get to exactly the same value. If we were to round the two decimal places, both this number and the N number end up being 0.06 anyway. So we can see that equilibrium is back established. So that Le Chatelier says, if we increase the concentration of a reactant, the reaction is going to shift to the right to produce more products so that the K value can be reestablished. If we decrease the concentration of the reactant, the reaction is going to shift left to make more of it, because now we would have a situation where if we decrease the concentration of a reactant, the Q value would be bigger than the K value, and now again we can see that the arrow points to the left, which means the reaction would shift to make more reactants. So this is the general rule of thumb. If you increase one side, the reaction shifts to the opposite side. If you pull or decrease the concentration of one of them out, then it will go to make more of that. So a way that we can use to justify your prediction, if you're asked to justify which way the reaction is going to shift, the best way to do that is to do a Q versus K comparison. Another way you can do it, a second way, which a lot of you did in the lab, because we hadn't talked yet much about Q versus K, is utilizing reaction rates. If I increase the concentration of a reactant, I'm going to cause the rate of the forward reaction to be greater than the reverse reaction. By increasing the amount of reactants present in the vessel, I've got a greater number of molecules where there will be a greater chance of collisions and a greater chance of successful collisions. Therefore, the forward rate will be greater than the reverse rate momentarily until equilibrium can be reestablished. So that is how we can use a second way of explaining it. Either one is fine, but if you're asked to justify, you better talk about rate forward versus reverse, or Q versus K. So reaction rate before addition, we were at equilibrium. By adding more nitrogen, the forward rate increased because there's more successful collisions on the reactant side. That causes the reverse rate to increase and the forward rate to slowly decrease, and eventually they reestablish again and equilibrium is reestablished. All right, let's turn the page. So now let's apply that to this problem right here. Here's our equilibrium reaction, and by doing the following changes here, I'd like you to predict, will the reaction shift to the right to make more products, will shift to the left to make more reactants, or will have no effect on the equilibrium? Pause the lecture now and go ahead and do the same thing. All right, the first one, by increasing the concentration of CO, the reaction will shift in the opposite direction to produce more reactants. B and C are both no effect, and I'm sure many of you probably did this incorrectly. They're both no effect because they are both solids. And solids are not part of the K expression, so changing their concentration will have no effect on the equilibrium. However, C, you do have one small caveat, and that is we cannot remove all of it. If we remove all of it, then the reaction would have to shift to the left to make more of it, because you got to have some of it present in order for the reaction to be in equilibrium. But changing the amount of reactant or product, if it's a solid or liquid, will not have any effect on the equilibrium expression as long as there's still some present. D again, if now I remove a product, the reaction will shift to make more of it because some of it has been removed from the vessel. Okay? All right, the next application. What happens if we change the pressure? Changing the partial pressure is the same effect as removing or adding a gaseous product. So if I increase the partial pressure of carbon monoxide in the above problem, that is the same effect as increasing its concentration. So changing the partial pressure of it just means we're adding more molecules into the vessel, which is the same as changing its concentration. If we add an inert gas, if we add a gas that is not part of the expression and it doesn't affect the concentration of one of the other substances, it will have no effect on the equilibrium. This is specifically when we typically add a noble gas, because a noble gas is inert. But if they say they add a gas and it has no effect or it doesn't react with any of the reactants or products, adding it does not affect the partial pressures. And again, in the equilibrium expression, it's the partial pressure of the substances that's part of the expression. So putting in a gas that while it might cause the total pressure increase, it doesn't affect the partial pressure of the gas, and therefore it doesn't have no effect on the equilibrium. Lastly is changing the volume. When we change the volume of a container, what we really do is do the same thing. By decreasing the volume, it's the same thing as increasing the molarity or concentration of the substance or increasing its partial pressure. So reducing the volume has the same effect as changing its concentration, but it actually affects all of them. Now, you'll notice here, there's a small little result that we always get from it, and that is when the volume is reduced, the reaction will shift or go to the side where there is less gas. And if we increase the volume, the reaction will shift to the side where there is more gas. And the reason that there is, let's say I have a reaction of A producing 2B. The equilibrium expression would be the concentration of B squared over A. If I reduce the volume of a container, that means I'm going to increase the concentration of B and A. I'm going to increase both of them by the same effect. But you would think that there would be no effect. But the second one is, in this case, is squared. So it has a much bigger effect on it because there's more molecules of gas. And therefore, reducing the volume, there would be a greater effect on the product side, which would cause the reaction to shift away from it. In essence, we get the result that we just talked about. When we decrease the volume of a gaseous reaction, that changes the concentration of all the substances. Whichever side of the reaction has got a greater number of molecules of gas will have a greater impact in changing its concentration, and therefore the result will be it's always going to shift to the side that there's less gas. So reducing the volume changes the concentrations of all the substances, if they are gaseous. All right, so pause the lecture now, and I'd like you to go ahead and predict which way each of the following reactions will shift based on changing the volume, and I think they're changing the volume by reducing the volume. So if we reduce the volume, which side will each of the reactions shift to? All right, the first two should shift right, and that's because in the first one we have 6 moles of gas going to 0 moles of gas. So if I reduce the volume, it's like increasing the concentration of chlorine. It's the only gas present, and it's going to shift to the side where there's less gas. Okay, B, same thing. We have 2 molecules of gas on the left, 1 on the right, so it's going to shift right. Letter D, it's going to shift to the left because there's more molecules of gas on the right side, so it's going to shift to the left. And C, there's no effect because they have equal amounts of gas. Both sides have 4 molecules of gas, and therefore the reaction will not shift in either way if the volume is reduced. It'll have no effect on the equilibrium constant. All right, the last one is looking at temperature. Temperature is the only variable that affects the magnitude of K. All of the other variables, changing the concentration, changing the volume, the reaction will shift, but the K value will always go back to what it normally was under the current set of conditions. If temperature changes, K changes. And this is the rule of thumb. If a reaction is endothermic, increasing the temperature will increase the magnitude of K, and therefore increasing the temperature will cause product formation to increase. The opposite is true. If it's exothermic, increasing the temperature decreases the size of K, which means product formation will be reduced. And because if I did the reverse reaction, if it's exothermic to the right, it'll be endothermic to the left. So therefore, increase in temperature is going to cause the reaction to favor the side which is endothermic and push it to the opposite side. All right. So by changing each of the value of conditions, we'll be able to shift the reaction based on the current set of conditions. So a justification of something would be if you know that a reaction is endothermic, and they say what's going to happen to the amount of this product if the temperature is increased, you would justify and say since the reaction is endothermic, increase in temperature causes an increase in the magnitude of the K value, and therefore the amount of product that is present will increase as the temperature goes up. That is a way you could justify to earn full credit on the national exam. Okay? All right, so I'd like you to pause the lecture one last time and go ahead and see now how each of the following variables, and they all have different, go back to different things with changing concentration or pressure or temperature. See how each of the values will change based on the current reaction of 1 molecule of N2O4 producing 2 molecules of NO2. All right, letter A should go to the right because we've increased a reactant concentration, which is going to drive it right. Okay. In the next one, we have removed some of the product. So if we've removed some of the product, the reaction has to shift to make more of it. All right. In letter C, N2 is not part of the equilibrium. And we'll assume that N2 would not react with either N2O4 or NO2. And therefore, adding something that doesn't really cause an increase or decrease of the other gases is not going to have any effect on the equilibrium. Volume. The volume is increased. We talked about reduction, but increasing the volume causes the concentration to decrease because it's the same number of molecules but in a bigger volume. Both concentrations change, but again, the one with more molecules of gas, the top one, the NO, the product, is going to have a greater change. So they both go down, but the top one goes down more, which is going to cause Q to be less than K. So the reaction will favor the side of more gas if the volume is increased. Opposite is true. If you reduce the volume, it'll favor the side where there's less gas. And lastly, the reaction was told to be positive 58 kilojoules, so it's endothermic. So decreasing the temperature causes a decrease in K. Endothermic is a direct relationship. So if it's a decrease in K, there's less product formation, and therefore the reaction is going to shift to the side of reactants, and therefore shift to the left. That is Le Chatelier. It's mainly going to be asked as part of an FRQ question, equilibrium. It's usually worth 1 point. On the multiple choice, you might have a couple questions in equilibrium. You just have to be able to predict which way a reaction will shift based on changing the concentration, changing the volume, changing the pressure, or changing the temperature. If you have any questions, please contact me. Again, thanks for listening.